In this video, we are going to look at Activity 1B, Heat Equations and Calorimetry. And to complete this activity, you should have your formula sheet with the equations for this unit. And it should look like this. So you should have this with you. You do get to use these equations on your quiz and your test in this unit. So the first problem says how many joules are required to heat 250 grams of liquid water from 0 degrees Celsius to 100 degrees Celsius. So we know we're going to be using our heat equation, Q equals m times C times delta T, with Q being the heat energy, m being the mass, C being the specific heat capacity, and delta T being the change in temperature. And so it says how many joules, and joules are a unit of energy. So I know that it must be asking me for the amount of heat energy. So this is what we're looking for. And we need to figure out what we have given. So we know that M is going to be the mass, so 250 grams. 250 grams. C, since it's for liquid water, we know that the specific heat of liquid water is 4.186 joules per gram degree Celsius. And that is a value that you do need to have memorized. And then delta T is going to be T final minus T initial. So our final temperature, we're going to 100 degrees, so 100 degrees Celsius is our final temperature, and from 0 degrees, so 0 degrees is where we're starting. So T final minus T initial will give us delta T, which of course is 100 minus 0, so 100 degrees Celsius. So now all that we have to do is plug these values into our equation. Our equation's already set equal to the thing we're trying to find, which is our heat energy, which is measured in joules. So we just need to do Q equals 250 grams times 4.186 joules per gram degree Celsius times 100 degrees Celsius. And then of course our units cancel, grams on top, grams on bottom, degrees Celsius on bottom, degrees Celsius on top, and we're just left with joules, which does make sense because we're looking for heat energy. So we just need to put this in our calculator real quick. Let's move this down so it's a little more visible here. 250 times 4.186 times 100. Whoops, I put something in wrong. Oh, I put a negative sign to enter, and that gives us 104,650, and the units are in joules. And since it asks for our answer in joules, this is our answer. We could put it in scientific notation if we wanted to, but it doesn't say we need to here. So 104,650 joules. And I'll go ahead just for practice. We can put this in scientific notation. So that would be 1.0, since there's two significant figures here. Well, and there's only one here, but we'll go ahead and do 2. 1.0 times 10 to the 5th power. 1.0 times 10 to the 5th joules, and that is equal to Q. So either way you write your answer is fine. Next, it says the temperature of a sample of water increases from 20 degrees Celsius to 46.6 degrees Celsius as it absorbs 23.64 kilojoules of heat. What is the mass of the sample? So in this case, we are looking for mass of the sample. So we have Q equals M times C times delta T, but we want mass to be by itself. So that means that we need to move C and delta T to the other side of our equation. So I'm going to do that by dividing by C delta T on both sides. Whatever I do on one side, I can do to the other. So now my C cancels, my delta T cancels. So we have M equals Q divided by C times delta T. So now we have our equation rearranged so that mass is equal to our other variables that we are given in the problem. So our value of Q, it absorbs 23.64 kilojoules, so 23.64 kilojoules of heat energy. But I know that I need to use joules in my problem, so I'm going to go ahead and convert this kilojoules into joules, just using dimensional analysis. So we have kilojoules, we're trying to get to joules, and in our chart of King Henry died by drinking chocolate milk micro nano, we have kilojoules, and we're trying to get to the base unit of joules, so that's kilojoules is going to be bigger, so 1 kilojoule is going to equal some number of joules, 1, 2, 3, 10 to the third joules. So we convert here, kilojoules is going to cancel out, so we're going to 23, I'll move this over so you can see a little better, 23.64 times 10 raised to, oops, I hit the wrong button, 10 raised to the third power. So that is 23640 joules. And that's what I want to use in my Q equals mc delta T when I plug into my equation here. So we have our value of Q. Now we need C, and delta T is going to be T final, T initial, and that should give us our delta T. So we have a sample of water once again, and we know that the specific heat of water is 4.186, oops, I can't write, joules per gram degree Celsius. Just incidentally, the reason that we need joules when we plug our value into our equation is because of the value for specific heat of water. It's in joules per gram degree Celsius, not in kilojoules per gram degree Celsius. You can look up other values for specific heat that they're given in all sorts of different units, but since it's kind of a pain to memorize a whole list of different values for specific heat capacity, it's generally easiest just to memorize this one and then make sure your units match what are in the units of your specific heat capacity, joules over grams degrees Celsius. So we want to make sure our heat energy is in joules, our mass is in grams, and our temperature is in degrees Celsius. So that way it matches our specific heat and our units will cancel correctly. So moving on, so we have our value of C. Now we need our T final. The temperature of the water increases from 20 degrees to 46.6, so our final temperature is 46.6 degrees Celsius, and our initial temperature is 20 degrees Celsius. So 46.6 minus 20 gives us 26.6 degrees Celsius as our delta T value. So now we have all of our values, we just need to substitute back into our equation, which we've already rearranged, so this is really just substituting in now. So M equals Q, so that's 23640 joules. And then that's the only thing on top, so we're going to divide by C times delta T, C being 4.186 joules per gram degree Celsius, and delta T being 26.6 degrees Celsius. So now we have degrees Celsius in the numerator here and the denominator here, and then we have joules on top, joules on bottom, so those cancel out, and we are just going to be left with grams, which that does make sense because we are looking for a mass here. So let's plug this into our calculator. I always like to substitute and put the top in first and then divide by everything on the bottom. So 23640 divided by, and I'm going to put my denominator in parentheses, so 4.186 times 26.6. Close my parentheses, hit enter. And that gives me 212.308 grams, but then I'm going to round a little bit because that's a lot of decimal points I ended up with. I could round to appropriate significant figures, but that would just be one significant figure here. So I'm actually going to leave my answer just as a whole number. So I'm going to put 212 grams. That equals my mass. and I will box that in from here. Now on a test or quiz, you should round to appropriate significant figures or do whatever the problem tells you to do. If it tells you to round to a whole number, round to a whole number. If it tells you to round to 2 decimal places, then of course in this case it would have been 212.31. So round however it is telling you to round in the problem. Let's move this up just a little bit. Our last problem here says the temperature of a sample of iron with a mass of 10 grams changed from 50.4 degrees Celsius to 25 degrees Celsius with the release of 197 joules of heat. What is the specific heat of iron? So if you may notice here, our temperature isn't going up this time, it's actually going down. And so this is important to note things like this in our problem, because when we figure out our change in temperature, it's actually going to be a negative change in temperature. And then when it says releasing 197 joules of heat, that means that that heat is being given off. And mathematically, we show a release of heat with a negative sign. So in this problem, the temperature of sample of iron with mass changes from this to this. What is the specific heat? So we are actually being asked to find the specific heat of iron. So we are asked to find C, and Q equals M times C times delta T. So we need to rearrange our equation to get C by itself. So I'm going to divide by M and divide by delta T. I'm going to do that on both sides. So M cancels out, delta T cancels out, and we're left with C equals Q divided by M times delta T. So now we need to find all of these variables we can substitute into our equation. Q is 197 joules, but it's a release, so it's going to be a negative 197 joules. M is 10 grams. And then delta T is going to be T final minus T initial, and that'll give us our change in temperature. So T final from this one to this one. So 25.0 degrees Celsius is our final temperature, and then 50.4 is our initial temperature. So our T final, I'm not so good at doing negative, it's in my head, so 25 minus 50.4 gives us negative 25.4. And that is our change in temperature, negative 25.4. So now all we need to do is substitute in our values. And just point of reference here, just kind of a way to check your work. We're looking for a specific heat in the end. And so specific heat will never be a negative number. So if you're asked to find specific heat and you wind up with a negative value in the end, it's likely, well, it's pretty positive that you missed a negative sign somewhere in the problem. So go back and check your work and make sure you have your negatives done correctly, because that will mess up your answer just by having a negative that you're not supposed to have or by missing a negative that you are supposed to have. So let's go through. We have C equals Q, so negative 197 joules divided by M times delta T, so 10 grams times delta T, negative 25.4 degrees Celsius. So as you can see, we have a negative divided by a negative, so we're going to end up with a positive number here. So let's go ahead and put this in our calculator. None of our units are going to cancel here. Joules over grams times degrees Celsius, that will be our unit in the end. And if you look back at our other problems, our units on specific heat are joules over grams times degrees Celsius. So this does make sense for specific heat capacity. So all we need to do is type this into our calculator. We have negative 197. And then, you can't really see that, so I'll move it over a little bit. Close the parentheses, and then we're going to divide by everything in our denominator. So 10 times, and since this is a negative number, I always like to put that in parentheses as well. So negative 25.4 close that set of parentheses, and then close the parentheses of my denominator. And I got 0.77559. 0.77559. I'm going to round this to fewer decimal places. There's 3 significant figures here, 3 there, and 3 there, 3 there. So I'm going to round to 3 significant figures here. 0.775, but the 5 is going to make that round up. 0.776, and my units, of course, are joules over grams times degrees Celsius. And that is my value of C. We box that answer in. In this next problem, it says a 6.52 gram coin of copper absorbed 64 calories of heat. What was the final temperature of the copper if the initial temperature was 25 degrees Celsius? And then it tells us the specific heat of copper is 0.092 calories per gram degrees Celsius. So you might notice that instead of having joules for heat energy, we have the units of calories. But this is okay in this case because our specific heat for copper is given in calories per gram degree Celsius, not in joules per gram degree Celsius. If it were given in joules per gram degree Celsius, we would either need to convert the calories up here into joules, or we would need to convert our calories per gram degree Celsius into joules per gram degree, or convert joules per gram degree Celsius into calories per gram degree Celsius. But since our units match up, we are okay to just go ahead and do the problem. In this case, we are looking for the final temperature of copper. So this is a little trickier. Instead of just using our Q equals M times C times delta T, we need to actually split up our delta T into T final minus T initial. So then we can find our final temperature. So we have Q equals M times C times T final minus T initial, and we need to get T final by itself. So we can do this algebraically, but the other option is to just find our change in temperature, and then say at the end we'll take our delta T value and we will rearranged as T final minus T initial. So we'll add T initial to both sides, and we'll get T final equals delta T plus T initial. So this, to me, is probably the easier way of doing the problem. You can rearrange this equation, this expanded form of our equation, to solve for T final, but I think it's a little bit easier just to first solve for the change in temperature and then substitute into this smaller rearranged equation. So that's what we're going to do. We're going to take Q equals MC delta T, and we're going to rearrange to get delta T by itself. So I'm going to divide by MC on both sides. So now we have delta T equals Q divided by MC. So we need to substitute in some values. Our value of Q is 64 calories. Our value of M is 6.52 grams. And our value of C is 0.092 calories per gram degree Celsius. 0.092 calories per gram degrees Celsius. So now I'm going to substitute this in. So we have delta T equals Q, so 64 calories, over M, so 6.52 grams, times C, so 0.092 calories per gram degrees Celsius. So we can substitute this into our calculator. 64 divided by 6.52 times 0.092, close parentheses, hit enter. That gives us a delta T of 106.695. But the problem is not asking us for delta T. We first should figure out our units. Calories cancels out, grams cancels out, so we're left with degrees Celsius. But the problem wants to know what was the final temperature. So we need to substitute this back into our rearranged equation up here. So we know that our final temperature will be equal to delta T plus our initial temperature. So our initial temperature, T initial, we need to find in the problem. It says the initial temperature was 25 degrees Celsius. So now we need to do T final. It's getting a little messy here, but that's okay. Equals delta T, so 106.695 degrees Celsius plus 25 degrees Celsius. And that will give us our T final. We just need to add those two things together. So 106.695 plus 25. And that gives us 131.695, which I'm going to round to 131.7 degrees Celsius. So that was a bit of a longer problem. It's really not a more difficult problem in terms of the concept, but it is a little more difficult in terms of the algebra required to complete the problem. Let's look at our next problem. It says a 12-ounce can of soda weighs about 450 grams. How many joules are released when a can of soda is cooled from 25 degrees Celsius, which is room temperature, to 4 degrees Celsius, which is the temperature of a refrigerator? So first of all, we need to make a little bit of an assumption here. Soda isn't something that we have a value for specific heat capacity for. So we have to make the assumption that soda is primarily made up of water, which is a pretty good assumption. Most of soda is made up of water. It just has a little bit of caffeine and acid and sugar added to it. So we're going to make the assumption that our value of C in this problem is going to be the same as the value of C for water. So it's going to be 4.186 joules per gram degrees Celsius. And it says how many joules are released, so we are of course looking for Q, so we don't need to rearrange our equation. Q equals M times C times delta T. So C, we also need M, and we need T final, T initial, which will give us our delta T value. 12-ounce can of soda weighs 450 grams. So that's our M, 450 grams. How many joules are released when a can of soda is cooled from 25 degrees Celsius? So that is our initial temperature. It's where we're starting at, to 4 degrees Celsius. So that is our final temperature. So to get our delta T, we want to do T final minus T initial. So 4 minus 25. 4 minus 25 should give us negative 21 degrees Celsius. So how many joules are released? So joules are not negative, but we are going to end up with a negative value in the end for Q because energy is being released. But when I get that negative value, I'm going to know that that negative just indicates that the energy is being released rather than absorbed. So when I report my answer, I'm going to put it as a positive number and just say that this number of joules are released so that I can convey why my value ended up negative when I typed it into my calculator. So let's go ahead and do this. We get Q equals M, so 450 grams, times C, 4.184 joules per gram degrees Celsius, times delta T, negative 21 degrees Celsius. So grams will cancel out, degrees Celsius cancels out, and we're left with just joules. So we need to put this in our calculator now. We have 450 times 4.186. Oh, I don't know why I put a 4 there. It should be a 6. 4.186 times, and I'm putting my negative 21 in parentheses. So I get negative 39557.7. And I'm not going to keep all these significant figures. I'm actually going to round my value to just a few significant figures. But I'm first going to rewrite this as a positive number of joules being released. So I'm going to do 3, 9, 5, 5, and I'm just going to round this to a whole number. 8, so 558 joules, and I'm going to put are released to explain why this value came out negative. So this is my value, my number of joules that are released from my can of soda when it's cooling down. The last problem on this page, let's see, one more. Says how many joules are given off. So once again, we are expecting a negative value coming out of our problem when 120 grams of water are cooled from 0 degrees Celsius to negative 25 degrees Celsius. And you might say, well, okay, at 0 degrees Celsius, water is no longer a liquid. It should be frozen by then. So you are quite right. That's why it gives us the specific heat capacity of ice, because once water's frozen, it does have a different specific heat capacity than liquid water. So the heat capacity that we need to use for this problem, our value of C, is 2.09 joules per gram degree Celsius. And it's given here because it's not a value you are expected to memorize. So how many joules? That's Q. Equals m times c times delta t, and it's already rearranged to give us q, so we don't need to rearrange our equation here. So we need m, c, t final, t initial, and delta t. So the mass of our water is 120 grams. A value of C is 2.09 joules per gram degree Celsius. Our T final, we're going from 0 degrees, so 0 degrees is our initial temperature, and our final is negative 25 degrees Celsius. So T final minus T initial, negative 25 minus 0 gives us negative 25. We're going down by 25 degrees Celsius. So we need to plug into our equation Q equals M, so 120 grams, times C, 2.09 joules per gram degree Celsius, times delta T, negative 25 degrees Celsius. And now we need to plug into our calculator. So 120 times 2.09 times negative 25, which I did put in parentheses. So that gives us negative 6270. And that is joules, because our grams cancels out, and our degrees Celsius cancels out as well. So this value is in joules. And this negative sign means that it's given off. So I'm going to convert this into a positive value. 6270 joules are released or given off.